As noted in previous slides, storm organization increases with increasing wind shear. Once the wind shear is sufficiently high, and provided that we have at least some instability, thunderstorm updrafts can begin to rotate. Thunderstorms with a rotating updraft are called supercells, and supercells are characterized by a nearly steady state, usually intense updraft. They are almost always severe, with wind, hail, and tornadoes all possible. Now, as mentioned in the previous slide, the definition of a supercell thunderstorm is a thunderstorm with a rotating updraft. You can get a sense for this rotation here in this time-lapse animation. Now, the primary hazards associated with supercells are large hail, damaging to destructive straight-line winds, flash flooding, and tornadoes. Note that while most tornadoes come from supercells, not all supercells produce tornadoes, and in fact, only about 20% of supercells actually produce tornadoes. Now, there are some labels that you see here in this imagery, and they are important cloud features which we will discuss in the next slide. Recall from the basic SKYWARN presentation that there were several key features of supercells that were discussed. Now, they included, just as a quick refresher, the updraft tower, striations, the rain-free base, the wall cloud, inflow bands, the tail cloud, and precipitation cores. Let's talk briefly on how storms interact with wind shear and ultimately become supercells. Now imagine that we have a tube of horizontal air and subject it to increasing wind shear, as you see here in the diagram. As you might envision, due to stronger flow at the top of the horizontal tube, it will start to turn and tumble. Now, what happens when we insert a thunderstorm updraft? Well, that tube of air becomes tilted and the updraft starts to spin. Now, as defined earlier, a thunderstorm with a rotating updraft is a supercell. Now, depending on the vertical structure of wind, the updraft may rotate either cyclonically or anticyclonically. As a general rule, supercells are more favored when the deep layer shear values approach or exceed 35 knots. I want to stress the next several slides will feature some radar eye candy. While it's tempting to report what you see on radar, remember, we at the National Weather Service can see the radar imagery. What we cannot see is what's outside your window, and that's where you, as a SKYWARN spotter, are pivotal to the success of our warning program. We are beginning to understand a lot more about the three-dimensional structure of supercells, and these conceptual models that we have of supercells date back to the late 1970s. Even with all the advances in radar technology and more frequent in situ observations, these models still hold true to today. Let's take a look at the schematic on the right, and we can see features such as the hook echo, the bounded weak echo region, and the echo overhang. And these signatures all imply supercellular characteristics, and they match up very nicely with the conceptual models, again, that date back to the 1970s. Now, the radar screen captures to the right really do show these conceptual models quite well, Now, this supercell just southwest of Stephenville, Texas, exhibits the BWER, or the bounded weak echo region, as well as the weak echo region, and in the cross-section, we can see the echo overhang. Now let's actually go through and talk about why these features are important. So remember, a rotating thunderstorm updraft is important because it promotes hail production, deviant motion, and offers a greater risk for tornado production as well. Now, if we examine the conceptual model of a quasi-steady state updraft in the top two left panels, we see that a quasi-steady state updraft allows for favorable hail embryo trajectories that keep these ice particles suspended for longer periods of time in the cloud. However, note the rain-free or precipitation-free areas in the diagram. This is essentially the weak echo region, and there's no precipitation particles available to scatter the energy back to the radar. And this is where we get the term or the name weak echo or bounded weak echo region. This is essentially where our thunderstorm updraft resides. We can see that, again, these conceptual models match up pretty well with our real-life example from our vertical cross-section from the Fort Worth radar down to the southwest near Stephenville. Now, the growth by accumulation of supercooled water drops on the ice hydrometeors, this is known as riming, can allow for these hail embryos to become larger and larger. And sometimes these thunderstorms can be very efficient at producing copious amounts of these larger hailstones. Now, once these hailstones become so large, the force of gravity is able to counteract or even exceed the force associated with the updraft, and as a result, the hailstones will fall down to the ground. Now, this picture that we see in the bottom left actually shows a greater than 3-inch diameter hailstone that was reported in parts of Erath County on this date. Another way that we can examine a strengthening updraft is the use of legacy and dual pole radar data. Now, in this example, we note a greater than 55 dB reflectivity core aloft at the 3.1 degree elevation slice, which translates to around 18,000 feet above ground level. In the base velocity image here in the top right, there are indications of a mid-level mesocyclone. If we take a look at the dual pole data, we see an enhanced area of ZDR with much lower ZDR values surrounding it. The melting level is around 10,000 feet, so this area of enhanced ZDR exists in temperatures below 32 degrees. This is where we have supercooled liquid water drops. This is also what we call a ZDR column, where we have liquid water being forced upward above the level of 32 degrees, so typically above this level it's colder. And when we have the updraft with an ability to generate supercooled water drops, this implies some vigor or strength to the updraft. Now, we do see depressed values of CC, which suggest non-uniformity of targets in the sample volume. We'll actually look at this a little closer by taking a vertical cross-section, as you see with the line, in the next slide. So taking a look at the vertical cross-section of that same storm, we see some interesting features. Note the blue line denotes the height of the melting layer. In the reflectivity field, we can see the bounded weak echo region indicating little to no returns in the updraft core, as all of the precipitation particles are being lofted above the freezing level. The updraft is so strong that it overcomes the force of gravity that wants to push the hydrometeors back down toward the surface. It is similar to attempting to throw things through a fan. And it's very, very hard to do, especially if those things are lighter weight. The center column shows this ZDR column. Horizontal hydrometeors are lofted above the freezing level because of the warm core associated with the updraft. Now, these liquid hydrometeors are lofted above the freezing level. As you recall, liquid hydrometeors, raindrops, or water-covered hail appear oblate to the radar, and the ZDR value is greater than 0. And then finally, the far right panel indicates a mix of hydrometeors just above the ZDR column, and that liquid water is being lofted upward into the vertical, where now there is the presence of ice as some of those supercooled particles freeze. Some other visual cues of a strong thunderstorm updraft, especially in supercell environments, is the appearance of the pileus cloud. Pileus is Latin for cap, and the appearance of this cap cloud may infer a weakening of the cap or a strengthening updraft. When initial updraft cumulus develops beneath the cap, it forms in a region of unstable air. Now, the cap represents a region of very stable air, and generally a region of very unstable air exists above the cap. Now, when the top of the thunderstorm updraft encounters the cap or this region of stable air, striated sheets of clouds develop on the top of the cumulus. Because the region is still largely stable, the upward motion associated with the updraft is met with a counteracting downward motion. Now, a strong, persistent updraft or pocket of updrafts will likely break a formidable cap as seen in the image here on the left. Now, the image on the right, however, this is a weaker updraft, and it is unlikely to breach the cap. Now, if we examine the storm that resulted in the multiple updrafts breaching the cap that we saw in the previous image, we see the end result of the updraft breaking the cap and thus initiating actual storms. And then sometime later, we see a very pronounced updraft tower with very, very vivid mammatus. Now, in this instance, low-level features are masked due to the lower sun angle. Let's bring it back to pairing some things we talked about in the basic SKYWARN presentation. Striations are a great way to visually identify a supercell. Now here's a time lapse here on the left with a long radar animation from the Fort Worth Sphinx radar paired together to see the storm structure visually as well as from a radar standpoint. Now, this was a pretty eventful day across North Texas, and supercell storms on this day, back in 2015, produced between 10 and 15 tornadoes. Now, most of these tornadoes occurred in very rural areas, and they were rated EF0s and EF1s. Cells on this day were also very efficient at producing not only large hail, as we saw in the image earlier with 3-inch diameter hail, but also copious amounts of large hail. So the imagery here on the left is from portions of Erath County on April 26, 2015, where there was a significant accumulation of hail, so much that it appeared as if it were snow. And note that this is indeed during the spring, as there is a fair amount of green leafy vegetation as seen in the imagery as well.